My name is Deepak Gupta. I'm working with Sanjeev Savapandit. And title of my talk is Stochastic Efficiency of an Isothermal Work-to-Work Converter Engine. And this work is in archive. One can look at it. Okay, so first we'll discuss what is heat engine. So heat engine is a machine which convert thermal or chemical energy into a useful work in a cyclic fashion. So here we have a working fluid that is like a gas and piston, and which is connected to heat reservoir. TH is the hot reservoir and TC is the cold reservoir, and the temperature is given like this. So it extracts heat QH from the hot reservoir, and it performs some work W, and rest of the heat it dumps into the cold reservoir, and the efficiency is given by the work performed over the cycle divided by heat extracted from the hot reservoir. So in the quasi-static or reversible regime, so the engine's efficiency is given by Carnot efficiency. It's a much celebrated efficiency. So for any other engine like which is not Carnot, so the efficiency is limited by this Carnot theorem. The efficiency is less than equal to eta C. But I'm not going to talk about this heat engine. So I'm just going to talk about kind of isothermal heat engine. So isothermal engine, it's not a heat engine. So there is only one heat reservoir. So okay, so that I'll discuss. So in macroscopic engine, so there are almost 10 to the power 23 particles. But in microscopic engine, there can be only one Brownian particle, and in that case, the fluctuations play a significant role. So in 2014, there is a Nature communication paper by G. Verley and Madhava group from University of Luxembourg. They published one paper that called unlikely Carnot efficiency. So people just assume that before that, okay, so Carnot efficiency may be the most probable efficiency, but they showed that the Carnot efficiency is not most probable. It's a least probable efficiency one can see in large deviation function. So they assume that, okay, for microscopic engine, so input and output power are assumed to be Gaussian distribution. So the efficiency will be output power by input power. So if both are uncorrelated and the mean is 0, so we know that if both are Gaussian, the eta will have Cauchy distribution. But in that case, they observed that, okay, so if they are not uncorrelated, if they are not uncorrelated, they are correlated, and the mean is not 0. And in that case, they calculated what is the large deviation function, and the large deviation function has this kind of form, where mu is the mean of these power, CIs are the correlation among them. Okay, so this is the example they have considered in that paper. So isothermal work-to-work converter engine, and so this is a constant. So what this? So you have a Brownian particle in a heat bath, and you have two load. You have one load that is applying constant force on the Brownian particle, that is F1, and you are just pulling the load with some force F2. Both forces are constant. Eta is the thermal noise coming from the bath, and this is a two-dimensional picture, and the mean of position is taken to be 0 of the origin of the two-dimensional. So this is a property of thermal noise. This mean is 0, and the correlation is given by this. So efficiency is like, okay, so what is the work done against the load force? That is minus W1. There is a gamma. Gamma is dissipation. It's the overdamped equation. Overdamped equation. So eta is minus W1 by W2. W1 is the work against the load force, and W2 is the work done by the drive force. Since F1 is constant, you can calculate exactly, okay, so this F1 dot xt, since this origin, because of initial condition, you will get only this part. Since xt depends linearly on thermal noise, so this is a Gaussian variable, so this is a simple, one can calculate what is the large division function, and one can put these values in the back, this one, and one can write what is the large division function. So they plotted this large division function, and this has very nice structure like this. So it has one most probable efficiency, so it has one maxima at most probable efficiency, and one minima at Carnot efficiency. So the Carnot in the sense that, okay, you apply some work, and you are just applying some work, and you are extracting some work, and there can be some dissipation also, but the dissipation you can reduce to at any level. So in the limit of very low dissipation, you can get the eta C equal to 1. So this is a kind of analogous to Carnot efficiency. So I have plotted for two perpendicular forces. So in that case, I plotted this. So, but one can argue that okay, so the structure of the large deviation function is that it goes to constant at large efficiency. So maybe the probability distribution is not normalizable. So what is the problem? So then I calculated exactly what is the probability distribution. So this probability distribution has some prefactor like phi eta t, and this, if I put this phi eta t there and compare to the numerical simulation, blue is the numerical simulation and red solid line is the analytical, this solution, and they matches exactly. And this shows that, okay, so this has a nice, I mean, this is normalizable probability distribution. Okay, so, okay, what are the references? So this is the same group, they calculated, okay, so what they assume that there are two-level system, and the system is jumped between two systems by using periodic deriving. And they calculated what is the large division function, and the large division function has same kind of structure that I have shown you earlier. This is a US Berkeley group. Grant, maybe probably he's joining maybe next few weeks, maybe. So I asked him also about this work also. So what they have done, so they used a two-level system, and the states are modulated by some driving. And in a cyclic fashion, they computed what is the efficiency, and they calculated full large division function and probability density of this function. This is Carroll from Belgium. So he used the same overdamped equation, but instead of constant force, he applied sinusoidal driving, and they calculated the full large division function and probability density, and they compared with experiment and simulation, and they got very nice result. This is Park. So what they have done, so they have two Brownian particle. They are connected by some coupling, some interaction, and they are just applying some non-conservative driving, and they calculated large division function, and they show that okay, this large division function is not as mentioned in a Nature communication paper. It has different structure. Okay, so what I have done, so in this 3 and 4, they mentioned that okay, what happens if you have non-Gaussian fluctuations, and in all of the previous works, so they assume that okay, input and output power satisfy fluctuation theorem. So as Shilpi told about this fluctuation theorem also. Okay, so what I have done, so I have taken the Brownian particle, and the load and the drive force both are stochastic forces that you are applying from outside. Eta is the noise coming from bath, gamma is the dissipation constant, m is the mass of the Brownian particle. So this is my engine. So this eta t and fi, both the average is 0, and the correlation is defined by this, where theta is the force of the load, theta is the strength of the load force, and alpha is the strength of drive force relative to the load force. So the work done, I'm observing work done with respect to temperature of the bath. So here f and v both are Gaussian variables, so w is not expected to be Gaussian. So it has some different distribution, so I have to calculate that one. So what is the stochastic efficiency? Stochastic efficiency as defined earlier, that is minus W1 by W2. Okay, so how to calculate? So first I will calculate the joint distribution, and I will perform a Dirac delta integral over that one, and then I have to calculate this integral, simple. So first I have to calculate this joint distribution. How to calculate that joint distribution? First we will try to write a Fokker-Planck equation for joint distribution, and I'll take the Fourier transform of the joint distribution that gives me characteristic function. This characteristic function is defined here. And there is a Fokker-Planck operator. And a beautiful thing is that you can exactly map this equation onto a quantum harmonic oscillator whose energy eigenvalues and energy eigenfunctions you know exactly. And then you know the exact solution for all time. But we are interested in large time solution, so we take the large time solution, so we put it here and perform the integral over final velocities and initial steady state distribution. And the characteristic function, you get this g lambda 1 lambda 2 e to the power tau t, and tau t gamma is some time scale, and mu lambda 1 lambda 2. Mu lambda 1 lambda 2 is the largest eigenvalue of Fokker-Planck operator. And this g lambda 1 lambda 2 is some kind of prefactor, which is important also. So this g lambda lambda 2 is g naught divided by some function of lambda 1 lambda 2, which depends on theta and alpha also. So this g naught is purely analytic function, but this function can be anything. It can have any sign. So we have to take care of all these things. So okay, so if I know this characteristic function, I'll plug it here and perform this integral I'll invert that integral and I'll get this, what is this form. First, we have to understand what is the analytical property of this thing. Okay, so what is analytic? So if you stay in this region, G lambda of lambda 2 is analytic. That means the function, this one, is positive. So there is no problem. But if you go in this region, this function can have any sign. So this has singularity. So you have to take care of about all the singularity. So calculating joint distribution, you have to take care of all the singularities and all. Okay. So first case, when G lambda 1 lambda 2 is analytic, this means this function is positive. So you can calculate the from this, you can just perform the saddle point integration and then you can get the Law division form of this distribution. And this Law division function satisfies fluctuation theorem. So this is, so I calculated what is the Law division function, and then I performed the other integral to calculate what is the efficiency, and this Law division function, where J eta is the Law division function. And this Law division function is not same as the Law division function earlier people have calculated. So this means the Law division function depends upon the system and what kind of driving I am using. So I am plotting this distribution with the simulation. The blue points are the simulation, and the dashed are the analytical curve. So they fit it exactly onto each other. Okay. So what about this? If G lambda 1 lambda 2 has singularities, so then fluctuation theorem will not hold for large W1, W2. Then this thing has two types of contributions. One is saddle point contribution, and other will be branch point contribution. So so if I know exactly this term, I'll put it here, and I calculate this saddle point integration over this one, and I can get what is the full distribution. Okay. So this is my task. So, but unfortunately, we were not able to calculate this exact branch point contribution. So we'll tell how to calculate that thing also in numerically here. Okay. So I have to do this integral. So do integral, so I have to do saddle point integration, saddle point integration. So saddle point will be in W2 eta plane. So I calculate saddle point and I plotted it W2 eta plane. So it shows this red region is the branch point region and the blue is the saddle point region in both cases. So if there is no singularity, so red region will not be there. So saddle point will lie only in the blue region. So I don't need to care about what is the branch point contribution. But in other case, if the saddle point crosses the branch point region, so I have to calculate the branch point region. So there are two possibilities. Either it stays in saddle point region, or it can lie on both regions. So in the possibility one, I don't need this branch point contribution. I'll just take the saddle point calculation and I'll fit. So I can fit with the numerical simulation, but in the other case, I need. So both these cases depends upon theta and alpha. So this is a modified phase diagram. That phase diagram I showed you earlier, that gets modified based upon that. So in this region, I don't need saddle point contribution. I don't need branch point contribution, but in this region, I need branch point contribution. So the possibility one, no need of branch point contribution. So I'll just take the saddle point solution, I'll put it here, and I'll just compare it with the numerical simulation. It matches exactly. In the possibility 2, so we had this problematic term. I took it, I put it upstairs with this part, and I define some function in this, and I perform a numerical saddle point integration, and I calculated what is the distribution for efficiency, and I compared with numerical simulation. It matches exactly. Okay, so this shows that, okay, so even in the case of stochastic driving, so we can get Law division function and probability density function, and the structure of this Law division function is similar to the structure that they have shown in Nature Communication paper, but the Law division function had different property, different functional form. Okay, so so I have some open questions. Okay, so when input and output power are distributed according to Gaussian distribution and the joint distribution satisfies fluctuation theorem, the physical interpretation of this stochastic efficiency is explained in PRL paper. This is by Macroscopic, Esposito, and G. Verley from University of Luxembourg. They explained it. But what about in this case? In this case, fluctuation theorem doesn't hold always. So how to explain okay, what is going on here? So they told that, okay, so if you go here in this one, This one. So this is okay. We can see this. So this is Carnot efficiency. Beyond that, whatever you are getting, that is coming from the negative entropy production of the system, and this side is the very good for the positive entropy production. So they explained with the entropy, but in our case, fluctuation doesn't hold. So how to explain this? That's not clear, and that's kind of open challenge for us. And the other thing that okay, so if you have a if you want to calculate the distribution of some stochastic variable p omega t from the characteristic function, then you have to calculate both branch point and saddle point contribution. So both branch point and saddle point contribution are calculated exactly in this paper. So this is by our group, Sanjeev and Arnab, they calculated exactly. But what about in this case? So I'll just tell briefly what is going on in this case. So if you have one stochastic observable, so I have this kind of form. So this can have some kind of this structure. So if I have to invert that characteristic function using inverse Fourier transform. Where this so if this singularity is not there for some specific value of parameter, then I can perform saddle point integration. If this is there, then I have to calculate in complex lambda 1 lambda 2 plane. So these are the points within which the saddle point moves. This let's say lambda negative and lambda plus, and saddle point moves. And let's say this singularity is here, this lambda a. Then if I'm crossing here, then I have to compute both contribution. In this region, I have only saddle point contribution, and this one I have branch point contribution. So this is very I mean it's explained in that PRE paper, but in my case it's very difficult for us to how to calculate that part. So in my case, I this g lambda is now g lambda 1, g lambda 2. So this has this analytic part, and there is some problematic part that I am defining f negative lambda 1, lambda 2. So in this case, this is only one dimension, and I am just writing in a complex space. So in this one, so I have this lambda 1 and lambda 2, and it becomes 4-dimensional space. And this region, earlier it was like on real line, now it becomes like an ellipse. Earlier it was a branch point, now it's a branch contour. This one. So the saddle point moves from here to here. So how to calculate this thing, that is not clear to me and to us also. So this is kind of open question for us. This is all about. Thank you.
You had only one hit path, so how do you define Carnot efficiency?
So the Carnot efficiency is like, okay, so you are applying it's kind of work source. So you're applying work, and you're lifting something. That is also work done against the load force. So the efficiency is like W1 by W2. So there can be any dissipation also. In that case, the eta is always less than 1. But in the limit of dissipation going to 0, so eta goes to 1. So this is called an analogous. In literature, it's called analogous of Carnot efficiency. It's not exactly Carnot efficiency.